Okay. Good afternoon, everyone. Whenever you are curious, you find lot of interesting things to do. I am Supriya Nayaka hosting this program. I welcome everyone for 88th episode of Creactive Online Talks. Creactive. Creactive is a group of people who are eager to gain new knowledge. Knowledge Square is our tagline, sharing of knowledge increases our knowledge. Vision of Creactive is to build constructive thinking on various domains. We mainly focus on non-textual, non-academic, non-syllabus related concept. Creactive is a platform to the resource person to present their views, discoveries, and many more. And we are thankful to all our resource person for engaging us with their knowledge. Every Saturday, we organize online talks around 3 to 4 p.m. on Zoom platform, and we live streaming our program on Creactive GBD YouTube channel. Today's Creactive topic is Living with Our Star, the Sun. To present this, we have Dr. K. Shankara Subramanian, sir, with us. I welcome you, sir, and I call Srinath, sir, to introduce today's speaker. Over to Srinath, sir.
Good afternoon and namaskaram. Is my voice audible?
Yes, sir.
Okay. Thank you, Supriya, for giving me this opportunity to introduce Dr. K. Shankar Subramaniam. He obtained his PhD in physics from Indian Institute of Astrophysics in Bangalore. His research areas of interest are solar magnetic field, optics, and instrumentation. He has more than 10 years of experience in optical, NIR, UV, and X-ray instrumentations for ground as well as the space-based observatories. In different capacities, he has contributed to AstroSat, Chandrayaan-1, Chandrayaan-2, the prestigious missions of ISRO to the moon. Currently, he is playing an important and active role in the upcoming Aditya L1 mission as a principal scientist of this mission. He is also a principal investigator for one of the important payloads of Aditya. He has more than 100 papers, national as well as international journals, and he is an active member, and he has guided many students towards PhD students. He is also one of the important colleague in our ISRO involved in the Aditya mission. It is my special privilege to introduce Shankar Subramaniam to the August audience. Thank you for giving me this opportunity. Over to Supriya.
Thank you, Srinath, sir. Over to Subramaniam, sir.
Yeah, thank you, Supriya, and thank you, Srinath. And let me first of all thank Srinath for giving me this opportunity. And I think this is a wonderful forum for, taking our work to the general audience. And I'm not being a scientist. I don't know how much I will be able to convey the informations. I am going to keep the informations as low as possible. And since I don't know the range of audiences in this particular forum, I will try to provide as more information as possible. And if any queries are there, you please let me know. I will try to answer as much as possible. Let me try to share the presentation and is it coming?
Yes, sir.
Okay. Okay, somehow it's not going into the slideshow mode. Okay. So are you able to see it?
Yes, sir.
Okay, good. So the topic of my today's presentation is going to be living with our star, the sun. The reason I chose the topic is, of course, I work in this particular area, trying to understand our own star, the sun. And of course, there are a lot of important informations which is provided by the sun, which I will try to touch upon in this particular talk. And I also touch upon, from ISRO's point of view, what we are trying to do to uncover some of the important informations provided by the sun by using our upcoming mission called Aditya L1. So where we are in our galaxies, I don't know, many of you would have already gone through this. If you look at it on the right hand side picture, you see this is a kind of a cartoonistic way of representing our galaxies. It's not an actual image, but it's a cartoonistic representation of the galaxy. And the size of the galaxy is something close to 27 kiloparsec. I mean, that is the size of the galaxy. Just to put everything in perspective, I'm just trying to give you some numbers here and try to link it to some numbers which we probably relate it to. So 1 parsec is something close to 3 light years, which is about 10 power 13 kilometer. And if I have to link it to the distances what we see on the Earth, that is, if I travel between south of India to the north point of India, that is from Kanyakumari to Kashmir, if I travel by air, I have to travel something around 500 crore times to cover 1 parsec. That is the kind of distances which we talk about in astronomy. And of course, once you have such a large distances, 27 kiloparsec, you know how much time it is going to take. So it's very clear from these numbers that it's very hard for us to roam around in the galaxies with the current technology because of the humongous amount of distances involved in it. And where do we live? It's in a very small area, maybe around 75% from the center of the galaxies. We live in a small place called a solar system. In one arm of the galaxy, and that is what is marked here. And in this area, we also call this as a heliosphere. I just want to put the definition of heliosphere. Heliosphere is a region of space encompassing the solar system. I mean, of course, all of us know about the solar system, and in which the solar wind has a significant influence. So I'll talk about what do we mean by solar wind, and how does the solar wind influences the heliosphere. And what you see here as a movie is basically our galaxies, and we live inside the galaxy, as I told in the previous picture, in a small cocoon, which is what is shown here. What you see at the end of this movie is the kind of heliosphere what we live in. So this is the kind of heliosphere where the whole of our solar system is encompassed in it. Is it a new region? No, it is not, because we have seen such a phenomenon in the astronomy. We call that as an astrosphere. And what on the right hand side, what I have put is a few examples of astrospheres observed from different galaxies, and which is also depicted in the figure caption. So heliosphere is nothing new. We do see such an astrosphere everywhere in the universe, and heliosphere is important to us because we live in the heliosphere. So anything happens in the heliosphere will have some implications on our life. Here is another way of representing the heliosphere, which probably kind of a more known way to many of us, which shows the sun on one side and all our solar system up to Neptune. Of course, Pluto can be included. And we also see the end of the heliosphere is typically called as a heliopause. I mean, that is the region where the solar wind and the stellar wind, probably in the interstellar space, they do get mixed up between the two systems. So again, I come back to the distances. So 1 parsec is roughly about 200,000 astronomical unit. Astronomical unit is the distance between the sun and the Earth. And typically, if you want to link it to the distances which we know, again, going by the travel distances between south of India to the north of India, 1 AU is something like 50,000 times if you travel between South Point and the North Point of the India. So that's a typical astronomical unit, and heliopause is somewhere around 100 AU distances. But these are all we come to know much better because of the launch by Voyager, launched by NASA a long time back, the Voyager system, which crossed our heliopause, and currently it is traveling in the interstellar medium somewhere in this place. And that has given us a lot of information about what do we mean by the termination shock and what do we mean by the heliopause distances. Now, heliosphere also, we split them into two. One we call it as an inner heliosphere. The heliosphere which is below 10 AU is called as an inner heliosphere, which falls somewhere around Saturn. And the distances above 10 AU, we call it as an outer heliosphere. Of course, this 10 AU doesn't have any sanctity number. It's just a number for our own convenience to separate the two inner and outer regions of the heliosphere. Here is some example of the Voyager observations. I just want to bring it to your notice that when I defined the heliosphere as a sphere of influence of the solar wind, I'm going to cover some aspects of solar wind, as well as some of the dynamical events which happens on the sun. So though the solar wind gets confined within our heliosphere, there are these dynamical events which can propagate outside of the heliosphere and can reach up into the interstellar medium. Interstellar medium is the medium between stars, whereas interplanetary medium, we call it as a medium between the planets. So the outside of the heliopause is the region where we call it as an interstellar medium. So when the Voyager crossed our heliopause somewhere around 2012, you could see that there are a few places in its travel as it travels in the interstellar medium. You can see there are few places where there is a enhancement in the densities. These are all representations of the densities of the medium in the local region. And these enhanced densities have a link to the coronal mass ejections which is happening on the sun. I'll be covering about some aspects of these coronal mass ejections and the solar wind when I come and discuss about the inner heliospheric region. So in essence, what I'm trying to say here is the sun's influence is not only within the heliosphere, it does crosses the heliosphere and goes into the interstellar medium. That is what the new information which Voyager has given us. Where does Aditya comes in? So Aditya, as you all know, is going to sit in front of Earth in the Sun-Earth line, and it will be sampling the region between the Sun-Earth line. So the box, what I have shown you is the region where Aditya will be looking towards that particular region. It's a very small region what we are looking at, but it's an important region because many of the events happen in this particular region do affect our own planet Earth. Okay, before going into much details, there is always questions from the younger colleagues. Why do we have to study the sun? And of course, we know that, sun is an important star for us because that is a star where we derive most of our life out of it. So so all the energy sources what we have on the Earth is coming from the sun. So life on Earth is thrives based on the solar energy. And if sun doesn't exist, and I don't think life will be there on Earth due to the source of energy, as well as the heat energy what is needed for human being to survive on Earth. And as a physicist, I'm hoping many of you are teachers of physics. Many of you are students of physics. As a physicist, I think sun plays a major role as a unmanned laboratory. A lot of physics, what we know currently on the Earth, has also been unraveled when observed with the sun. We also call it as an unmanned laboratory because there are certain physical conditions which exist in the sun, which is not feasible to mimic on the ground. So certain conditions where your physics laws and physics you want to test it, which cannot be done on the ground, can also be done on some objects like the sun. So we call that as an unmanned laboratory. And of course, sun being closer to us, it is used to understand other stars. When I say other stars, other sun-like stars, because we know that star has a gamut of different characteristics, different energies involved. Sun-like stars will behave like a sun. So whatever we understand from the sun, we can extrapolate to sun-like stars, which is not possible for us to resolve it due to the distances with which the stars live from us. And same thing is depicted here, only star which can be resolved to greater details. Some of the finer aspects of the stellar evolution is captured on the sun and then interpolated to the stellar physics. And of course, as I told you, it does have certain effects on the Earth atmosphere. And with a lot of technology now in space, it also has certain effects on those technologies. So that's another important aspect why ISRO wants to study the sun. Not only, apart from the physicist, technicians also are interested in to study the sun in order to understand its implications on the technologies and its effect on the solar events effect on these technologies. Gives a lot of information for the space scientists. Sun is a normal star. It's nothing very special star. It's a very average star, which is a middle-aged star. Almost half of its life is over in the main sequence, and its spectral type is a G2 star. And it's a special star for us because it's the only star on which we can resolve the spatial scale, as I told you earlier. And it also provides the most of the energy what we have it on the Earth. And the sun is a special star because it provides us a laboratory for certain tests which we cannot done it on the Earth. This is also many questions which I get it from students. Do we need to take solar physics or astrophysics as a specialized course? I would suggest not to enter into it so early in your career, because any astrophysics or solar physics is nothing but the applied physics. So what you learn as your physics and mathematics is applied to astrophysics and solar physics. So here is a few examples. What we study about atomic and molecular physics, for example, the spectroscopic signatures of the sun is nothing but a lot of atomic and molecular physics goes in there. The fundamental forces, the gravitational force, is being studied with objects like the sun. Plasma physics and cosmic rays and interstellar medium, they all are linked to the basic physics. Of course, nuclear physics. Nuclear physics is the nuclear fusion is the source of any of the stars what you see in the sky. And so understanding nuclear physics is an important element to understand the energy sources of any of the stellar objects what you see. So my one suggestion would be to take up the basic physics and mathematics, which are the important ingredient for you to get into the astrophysics and in particular solar physics. So do your basic physics pretty well in your elementary schools as well as in your bachelor degree. Yeah, very brief about the sun. How does the sun sustains its energy? What you see here is the structure of the sun. There is a core, which is where most of the energies get generated. If you see my cursor, the core is depicted here. That is where most of the matter lies. I mean, the high density of matter lies in the core, where the nuclear fusion happens, hydrogen fused into helium. And while doing that the process, it emits a lot of energy. And that is the energy which is being transported in the different mechanisms. You can see the radiative zone and convective zone. These, again, you would have studied in your physics as a radiative energy transport and convective energy transport. So through the radiative and convective energy transport, the energy which is created in the core is carried into the surface, and then from the surface it is given to the other planets and the Earth. And typically, the solar atmosphere we classify into 3 to 4 major areas. The photosphere, as you can see here, and photosphere is the region where you can see the sun with the visible light. I mean, when you see the sun, not with a naked eye, with the protective glasses, when you see the sun, what you see as an yellow ball is the photosphere. We call that as a, technically we call it as a photosphere. That is a region where the photons get ejected from. That's why it's called as a photosphere. And the region above it, where you see is a bit more corrugated and yellowish in color, and you also see bright structures on it. We call that as a chromospheric region. It's also marked here as chromosphere. And the regions which is above the chromosphere, we call it as coronal regions. You also see you also see that there are few structures. Of course, you would have studied by now. I think there are sunspots. The dark structures, what you see here is a sunspot. And the same dark structures, when you go into the chromosphere, becomes like a bright structure. We'll talk about it, why it changes its character from dark to bright.
Sir, 1 minute, sir. I'll
Yes,
mute
yes.
everyone.
Yeah.
You are also muted, sir. Just unmute it, sir. Okay.
Okay, can you hear me?
Continue. Yes, sir.
Yeah,
Yes, sir.
yeah. And you also see a feature, we call it as a prominence, which stands out above the solar surface. I mean, it's like you are flying in an aeroplane above the Earth's surface. There are plasma which is flying above the solar surface. And since the plasma is cooler in temperatures, you see it as a dark feature here. And this we call it as a prominences in the solar atmosphere. So there is a gamut of structures what you see in the solar atmosphere, which is an important information for us to understand. And they are the one which are dynamic. I'll talk about it in a minute. Here is a typical average temperature structure, what you see on the sun. So you have a temperature starting. I mean, interior of the photosphere, temperature starting around 10,000, and by the time it comes to around 5,000 or 6,000, that's the place where we start to see the visible surface of the sun. And it keep on decreasing, the temperature keep on decreasing up to a temperature minimum, maybe about say 3,000, 3,500 degree Kelvin, and then it starts to increase. So this is a puzzle which is being addressed currently now. We call this as a coronal heating problem. That is, we know from the second law of thermodynamics, when you go away from the heat source, I mean, if you have a hot rod in your hand, when you go away from the hot rod, the temperature is supposed to decrease with the distance. It does it up to certain distances, and then after that it starts to increase and goes all the way up to the up to million degree Kelvin in the corona. This is a puzzle which we are trying to understand. There are few theoretical models, there are few observations which indicates what could be the sources of these, but we are still yet to fully solve this particular problem. Again, just to appreciate what we are talking about in this number, what I have marked here is the melting point of some of the metals. You see the melting point of iron, which is roughly around 1500 degree Kelvin, and the melting point of tungsten, which is the strongest metal, which has the highest melting point, is somewhere around 3500 degree Kelvin. Okay, so you have a huge temperatures in the solar atmosphere, starting all the way from 3500, which is the typical melting point of tungsten, and goes all the way up to million degree, 10 power 6 degree Kelvin. It's a huge temperature. On the other hand, on the other axis, what you see here is the mean density of the atmosphere, and they are pretty low compared to the Earth's mean density, which is of the order of 5,000 kilogram per meter cube. So the density is lesser than the Earth's atmosphere. I mean, the density of the photospheric regions, which will fall somewhere around a certain height in the Earth's atmosphere, maybe around 100 kilometers or so. So we do have a lesser density, higher temperature. So this is what I said. It's not feasible on ground to have a condition where you have a high temperatures and low density. Certain physics, what you do with high temperature and low density, cannot be revealed on the ground because we don't have such a conditions on ground to have such an environment. So which is available on the sun and other stellar systems. So we can do certain physics which cannot be revealed on the ground, can be revealed in the sun's atmosphere. Here you see, we do have solar observations, plenty of solar observations, starting from way back from Galileo's time, from ground, as well as currently with many of the space telescopes, which is giving us a lot of information about sun. Here is a collection of the solar images taken at the same time, near simultaneously, but at different filters. When I say different filters, basically we sample different temperatures on the solar atmosphere. As I told you, the temperatures varies as a function of the height above the solar atmosphere. So if I have an observations at different temperatures, basically it tells me at what height such features are seen. So I'll start from here. This is this 4,500 angstrom, which is what the typical photosphere, what you see with looking at the photosphere with a visible light. And as you go slightly higher temperature, so this is at 10,000 degree Kelvin, you can start to see certain features. The sunspot, what you see here, and the surrounding regions are not as different as what you see it here. Basically, what it tells you is that the brightness from the quiet region drastically changes with the temperature, whereas the brightness of the active regions, which is surrounding the sunspot, has an enhancement compared to the quiet region. So you start to see the active regions coming brighter and brighter when it goes to higher and higher temperature. And you can see at 50,000 degree Kelvin, you can see that the sunspot becomes fully bright. And this is 6 million degree Kelvin, which is in the corona. And this is at 1 million degree Kelvin temperatures. So we have a structure which is seen at different temperatures, and they do change their emissive characters at different temperatures. Of course, this is not surprising. This is expected, but the amount of energy released in this process and relating to the temperature, they don't go one to one, and so that's where the very interesting physics which goes in to see how this brightness comes out in an active region. And this also has an implication of why the temperatures in the chromosphere and corona is higher compared to what is in the photosphere. So the whole research in solar physics revolves around this particular information. Okay, here I have just put a couple of movies about how dynamic the sun can be. So this is taken somewhere in 2003. It's well-known Halloween flare, and which is one of the highest flare in the last maybe decade or so. And this has provided lot of what you call geomagnetic storms, as well as a lot of trouble to the spacecrafts in which were in the space. Both are from the same what do you call same events. What I want to show you here is at the end of the event, if you look at it, you see the camera goes a bit fuzzy, in the sense you start to see a lot of salt and pepper type of pictures, which is nothing but the mass which is thrown out into the interplanetary medium from the sun gets into the spacecraft, and hits the camera. And the camera, which is made of your silicon wafers, which is your camera, what you see on your mobile phone too, are sensitive to these particles, and they start to deposit a lot of energy onto the detector. And if this energy goes above certain number, and it can damage the detector. And same thing for other spacecraft electronics too. If this energy deposition is more compared to what the subsystem can withstand, the whole subsystem can fail during this process. So that's where the importance of studying the sun and its dynamics play a major role for technologists like ISRO and other space agencies. I mean, last week, I mean, you would have heard this humongous news about the March 13th event, 2023 event. And this is the event what we have seen is one of the heaviest event. Fortunately, it happened on the other side of the sun, because sun is a sphere. What you see in one side is only one half of the sun. And this event happened on the other side of the sun. So most of the mass thrown out from this event has gone away from the Earth compared to what is seen on the Earth side. What you here see on the right hand side is the auroral effect of these particles, which has reached up to the Earth because of this powerful event, and created a geomagnetic storm. Of course, this geomagnetic storm is not as big as the 2003 Halloween event, because the 2003 Halloween event happened on the front side of the sun, where the Earth is facing, whereas this is facing on the back side of the sun. And a lot of these particles, I think we started seeing in the Earth's orbit as well as in the Sun-Earth line after a couple of days of the event, which happened on March 13th. And a lot of our instruments, which is orbiting now, has collected these informations, and we are in the process of looking at these data to understand this event in a better way. What are such events? I'm just trying to give you a few indications here. Of course, we'll go into a bit more detail. This event reached L1 around March 15th, and you can see that the magnetic field at the L1 point has started increasing, and stayed for increased level for a longer period. And that also shows that the density of the medium, I mean the density, when I say it's a density of the plasma which is coming from this event, has also increased and stayed for a longer period in the same systems. So these are the informations which we get from these events, and which are all vital for us to understand about the event and its implications on the Earth's systems, as well as the spacecraft systems. Of course, living on Earth, we do have protective layer, which is our magnetosphere. What you see here is a movie of the solar wind. which is coming from the sun. So I'll just pass it and go back and run it again. So these are the solar wind, which as soon as it comes and hits here, this we call it as a magnetopause, like what I showed you earlier, the heliopause, which is the region where the particle starts to deviate its directions because of either the density enhancement or some forces which doesn't allow the particles to enter in. Here in this case, it is the magnetic field of the Earth, which doesn't allow these charged particles, which are the plasma, which doesn't allow it to enter into the magnetosphere. It just deflect it to move around the magnetosphere. So we live in this particular cocoon, which saves us from getting affected from the solar wind. Of course, there are few particles which can enter through the poles, which are open field lines, and they are the one which comes and hits on the Earth's atmosphere. And what you see here is a kind of a volatile. As the energy starts to increase, the atmosphere starts to evaporate from the Earth. So many of the planets loses its atmosphere due to this process. Since we do have a magnetic field, the atmospheric loss is much lower compared to any other planetary system which doesn't have its atmosphere. I mean, its magnetic field. What is a solar wind? I mean, solar wind is a kind of a particles. I mean, what I showed you is a dynamical cases where you can clearly see the particles coming out. But I mean, there is a solar wind which is present all the time from the sun, and which basically throws out the plasma into the interplanetary medium of this order of 10 power 36 per second. And at this rate, if I mean, this is continuously throwing out this mass. I mean, even if it at this rate it throws out a mass and throws out the mass, we lose equivalent to one Earth mass to the order of 150 million years. So the mass loss is not very high, but we do have masses which is being thrown into the interplanetary medium. Whereas the CME mass, when it throws out, it is somewhere around 10 power 4 times higher than what you get from the solar wind mass. Of course, when you compare it with other stellar systems, our solar flare is not as high as what you get in some of these solar flares happens in young stellar systems. Of course, I mean, when sun was younger, I mean, maybe 1 billion year or before 1 billion year, it would have thrown a lot more mass compared to what it is throwing currently. So that we call it as a solar wind. And what you see here on the right hand side is the particle spectra from the solar wind. The x-axis is the energy of the particles. So when I say particles, the particles can be electrons, protons, or any ions. So that's why we call it as a per nucleon. Per nuclear means from one per one nuclear. How many is the number of particles it is? Okay. So what we see here is solar wind covers this main particle populations, and as and when the CMEs and solar energetic particle happens, we cover in the higher energy part of it. So the CMEs and the solar energetic particles do throw a lot of high energy particles into the interplanetary medium compared to the solar wind particles. So that is the takeaway which I wanted to give it to you for from this particular slide. Now, are they going to affect the Earth? So here is a composite movie from multiple missions flown so far, and you will really appreciate what is going on in the interplanetary medium. So what you see here is the sun is in here, and you see a coronal mass ejection, which is ejected into the interplanetary medium, and as the mass ejections propagates it reaches to the Earth, and of course it reaches away from the Earth too. So it does affect all planets, not only the inner planet as well as the outer planet, including Jupiter's and Pluto systems. So that's why the sun's influences get felt in the inner heliosphere much more than in the outer heliosphere. Here is a real observations taken from our own Wuti radio telescopes, how the disturbances propagate. And what you see here is the disturbances emanating from the sun. And this is our Earth, which is sitting 1 AU, 1 astronomical unit from the sun. And typically it takes about a few days to travel from the sun to the Earth. And you can see such a huge amount of disturbances which is propagating in the interplanetary medium. And these are the one which when it couples to the Earth's magnetosphere, and or if the satellite system which is away from the Earth's magnetic field can start to seal these kind of particles in their system, which can affect the system as well as the subsystems, and it can even kill the subsystems to make the satellite not working as intended. Here is another view of the same thing, but very close to the sun. Fortunately, we have recently Parker Probe Plus, which was launched very close to the sun. And what you see here is the mark here is the Parker Plus, which is sitting very close to the sun, and how the events does come and hit the satellite systems pretty heavily. So these kind of disturbances are there everywhere in the heliosphere, and as you go closer to the sun, and you start to the densities will be higher, and you start to feel the effect more and more. So just to consolidate what I told you about the inner heliosphere, here is the cartoon of it. So we have the mass ejections coming from the sun, which is maybe in the form of flares or coronal mass ejections. And these mass ejections starts to travel in the interplanetary medium. And of course, as I said, the sun has a magnetic field. So the interplanetary medium also has a magnetic field. Since the sun is rotating, the magnetic field also starts to rotate. And that's why you get this kind of a spiraling in the magnetic field, which is depicted as a spiraled line here. And this yellow spiral things is nothing but the particles which cannot cross the magnetic field, but it will have to hang on the magnetic field and move along the magnetic field line. That is basically, we know from our basic physics that a charged particle cannot cross the magnetic field, lines of forces. And so that is the one which will reach the Earth, and Aditya will stand between the Earth and the sun. And this would see both the coronal mass ejections as well as the particles which is reaching to the Earth well before well before it reaches the Earth. You'll start to see those particles which is coming towards the Earth. What is an L1 point? This is basically a point where the gravitational force of Earth and the gravitational force of Sun gets balanced. So you will have almost like a zero force here at L1, and Aditya will be orbiting around this particular orbit for us to look at the sun 24/7 without any interruption. So that's the advantage of being at L1. And of course, being away from the Earth's magnetic field, what we sample at L1 is the pure particle coming from the sun, without getting modified by the Earth's magnetic field. So to measure this, what we have is, a list of instruments. I call that as two category. Remote sensing. Remote sensing basically look at the photons, the light which is coming from the source. In situ is the actually measuring what is present at that particular point. So what I have listed out is the kind of instruments which we would like to have on any system to characterize the objects in a much more detailed manner. And what is marked as bold and colored words are the one which would be available on Aditya L1. Of course, doesn't mean that others are not available. We do have other space missions, which does carry other instruments along with their mission. We can collaborate with them and get those data. However, we have configured the Aditya L1 in such a way that with this existing payloads on board, we'll be able to characterize what we want to study from the sun. This is the stowed view of Aditya L1, which is currently being integrated at URAO Satellite Center. What you see here is the payloads. We have 4 remote sensing and 3 in situ payloads. This is the coronagraph, visible emission line coronagraph, VELC. And this is the SUIT, Solar Ultraviolet Imaging Telescope. And there are 2 X-ray payloads. One is sitting inside the deck, which is called High Energy L1 Orbiting Spectrometer. And one is sitting behind this hideout is the SOLEX, which is Solar Low Energy X-ray Spectrometer. And we do have a set of particle monitors called as ASPEX, which is Aditya L1 particle experiment. And we have PAPA, which is Plasma Analyzer Package for Aditya. And we also have a magnetometer, which is in a stowed condition, which will get deployed after we reach to L1 to measure the local magnetic fields. So while the remote sensing, 4 remote sensing instruments look at the sun, these 3 in situ payloads will look at what is happening in situ at L1. By connecting these 2, we will be able to know when the event happened on the sun and when the event reached at L1. And that will also tell us when the event is going to reach at the Earth with a proper estimation. This is the mission objective, to design, develop, and launch an observatory class satellite and be placed at Sun-Earth Lagrangian point for uninterrupted observations of the sun. This is the first Indian observatory class mission to study the sun and the heliospheric region. And these are the science objectives. I don't think I'll have to go into the details because I have one slide for each of the payload just to bring out what is the uniqueness of this compared to other missions. This is a table telling you what is the payload and what is its capability. It's basically, we look at the photosphere, chromosphere, as well as the corona by imaging, as well as the spectroscopy for remote sensing. And for in situ, we measure the protons, electrons, and heavier ions, along with the direction, which is an important information, which provides us the direction of propagations of the CME much better compared to unidirectional measurements. And we also have a magnetic field information, which tells us whether the CME events going to get coupled to the Earth's atmosphere or not. Here is an example. I mean, here is the flight model of VELC, which is realized and it's ready for integration. Which has 4 channels. 1 channel looking at the imaging. On the right-hand side, what I have depicted is the kind of images what you get from the VELC, basically the coronal informations of the eruptions. And it also carries a multi-slit spectroscopic measurements to study the plasma information, so like the plasma temperatures, plasma velocity, as well as the plasma densities. These are all important information for us to understand the physics behind these eruptions. Here is a solar ultraviolet imaging telescope. Again, the flight model. Currently, it is getting into the T&D activities. And it uses 11 different filters. As I told you, different filters samples different atmosphere. So we chose different filters so that we cover both photosphere and chromosphere with the same system. And one of the important aspect of this is, if you see, it covers this UV band, which is an important band for Earth's ozone measurements. The O2 and O3 band of the Earth's observations falls in it. And we know that this particular radiation from the sun do alter the ozone presence on the Earth atmosphere. So the variability of this particular band and associating those variability to the sources, which is currently not available from any of the missions. I mean, whether this variability is due to the sunspot, whether it's due to plages or any other active regions on the sun, is something which we look forward from this particular mission, which is not currently available from any other mission consistently doing this particular observation. And we know that the spectral variability is much higher in the lower band, which is depicted as your green line. That the variability is much higher in the below the visible band compared to at the visible band. And these two payloads, which are the X-ray payloads, so basically does the spectral informations of the or the energetic events, especially the solar flares, and talk about the thermal energy content of these flares, as well as the non-thermal energy content of these flares, which gives an indication about what kind of radiations which is going to come, what kind of radiations in terms of electromagnetic radiations, as well as what kind of particle population which is going to come and hit the L1 point. So the connections between the sun and the earth can be obtained from these two payloads, especially from the energetics point of view. And this is the aspects payload. It consists of multiple instruments placed at different orientations. You can see the orientations marked here. Each instrument is marked in different colors. So you can see that this is the Sun-Earth line. So you can see that the instrument collects informations of these energetic particles coming surrounding the Sun-Earth line, and hence will provide information about the anisotropy of these these particles which is coming from the sun, and provides us an information about the directionality of these events, and which will have an important implications on whether these events are going to come and hit the earth or going to miss the earth. And on the right hand side, it tells you what kind of energy ranges which it covers in this particular payload. And the plasma analyzer package also does this particle information, mostly the electrons and the ions, and it mostly samples the lower band of this energetic spectrum. So we do have a complete coverage of particle as well as the atmosphere of the sun, and hence we can comprehensively address the events, coronal mass ejection events as well as the solar flare events comprehensively with the Aditya L1. This is a magnetometer. Once its booms are deployed, we have two magnetometers spaced at 3 meter and 6 meter from the satellite, and this will give us an information about the magnetic fields of all three axes, because magnetic field is a vector quantity. We get the magnetic fields transverse as well as the radial magnetic field information, which has an important implications in linking the coupling of these energetic particles into the Earth's magnetosphere. Now, apart from this, we also do carry out the modeling because many of the observations what you do also require a kind of a modeling support, because Sun-Earth is a kind of a coupled system. So we cannot study only one object and then try to interpret everything in the heliosphere. So that's where the modeling comes into effect. So here is an example of a model which is done by the SESI team at IISER Kolkata to predict what kind of intensity distribution, what kind of corona you would see on the 21st August 2017 eclipse. And this modeling capability is currently available, and they can actually predict what kind of coronagraph images which visible emission line coronagraph can see every day, given the modeling capability of our own people. So this is something which we'll be utilizing it once our Aditya gets launched into it. And this also is an important element, because if you want to study the Sun-Earth connections, as I showed in the initial movie, if you want to really study the Sun-Earth connections, which we recently tried to carry out with our own mission Chandrayaan-2, here is an example of the sun, the Earth, and a moon which is sitting at the distance of 1.5 million kilometer. So what it shows is that the Earth's magnetic field, what you see here is a black color lines are the Earth's magnetic field. You can see how dynamic the Earth's magnetic field when there is a perturbations coming from the sun. And these do change the local particle populations, and that is something which we do observe from the Chandrayaan-2 data. So this is something which is being published currently, which is also available for you to look at these results. Okay, I'll just skip this because I think this is much more detailed than what it's needed, and just want to cover one important area, which is the support cell. See, though many of us know what to do with Aditya, people like you sitting in universities, institutes, colleges, for you to use the informations and the data available from Aditya L1, ISRO has put up a support cell which would act like a conduit between the users of Aditya L1 and the payload and science team of Aditya L1. So you get informations of the right informations from the payload and science team directly to you through the support cell. And they are also they are also going to organize training programs at different places within the country for the interested users to acquaint with the Aditya L1 proposal processing system, because Aditya L1, you yourselves can propose what you want to observe with Aditya. So there will be a proposal processing system where you can put up a proposal, and they will also provide you with the simulated data using data from other missions. They will also train many of the people who wants to get into the heliophysics and solar science. And they are the focal point for clarifications and queries from users related to any proposal submission form and the data related queries. And they also do the science support for the payload proposal processing system in close collaboration with the POCs. And they will also try to help the POCs to generate higher level data product, which is an important element for many of the other community to use. Say, for example, if a planetary scientist, if a person from Earth atmosphere wants to look at the event, he doesn't have to look at the Aditya data, analyze it, and bring out a product. I mean, he can provide. I mean, we can provide the product which he needs, like the electron temperatures, electron pressure, electron velocities, is something which we can generate and provide it to the other community, who can just simply plug in those numbers and start modeling it, and then try to interpret or look at the data which is coming from the data from other missions. So POCs can play a major role in this, and any other specific data products which is needed from the community, they can also provide, which is not available from POCs. They will be able to provide it. Okay, just to summarize and conclude, I mean, as I said, sun is essential for life on Earth, and probably it's for all planets. It provides a lot of advantages, including as an unmanned laboratory where many of the physics experiments can be carried out. And Aditya L1 carries 7 payloads. 4 of them are remote sensing and 3 are in situ, to study the dynamical nature of the solar atmosphere and also its influence in the interplanetary space and also on planets. Instruments are configured to take advantage of the missing observations in near future. That is, the observations what Aditya L1 would do is not available from any other space agencies currently or also in near future. And modeling is going to be an integral part of the analysis of the data from Aditya L1. And hence it shows a very promising directions to effectively utilize the data. And utilizing the uniqueness of Aditya L1 along with other missions is an area to explore, and this is being currently explored to maximize the multi-mission science advantages, which cannot be done either by Aditya L1 alone or by any other missions alone. So when we combine both missions together, there is a region of space which is not explored by individual missions that can also be explored with Aditya L1. And finally, we have plenty of opportunities for the science to come from Aditya L1. I would, I would throw my hat to all of you to come in and support us to bring the science out of it, and hopefully that can give you a career in the direction of solar and heliophysics. With that, I thank once again Srinath and company and for these opportunities, and I am here to take any of your questions. And if you want to ask me anything more details, the team has my email ID. Please feel free to contact me through email. Thank you very much.
Thank you, sir. If any questions, please raise the hands. I'll unmute them. If any questions? Okay.
Supriya, there is one hand raised. Please take it.
Yes, sir. Yes, sir. I am unmuted.
Yeah,
So please ask.
Yeah, I would like to ask the question, when is this mission going to take place? When is it going to be operational? Could you please tell about the timeline?
Okay, so the mission is planned to be launched this year, and typically it takes about 100 days to reach L1. It's roughly around 3 to 3.5 months for us to reach L1 and then there is a initial phase of what we call it, it's a mission pre-commissioning phase, where we check the health of the instruments, make sure all the data coming from the instruments go through the quality checks before it gets released for science operations. So from the launch phase to go to L1, it's about 3 to 3.5 months. And from there, the pre-commissioning phase and the release of the data is governed by the payload verification phase, which will happen maybe around 3 to 5 months of period. And then it becomes operational for science missions, and then the data would become available to the users.
Okay. Thank you.
Just for the benefit of the audience, the person who has asked the question, Professor B.A. Kagile, renowned astrophysicist from Department of Physics, Bangalore. Thank you, Professor, for asking the question.
Okay. Next, any questions?
There is a question in chat box. Can you take it up?
Yes.
Supriya, there was one question in chat box. Is it there still or it is disappeared?
I am checking, sir. I think.
Yeah, let me also ask one small clarification or some information regarding this 12-year cycle. Can you just briefly tell to the audience that what is it and where are we in the 2023 or 24, or by the time Aditya L1 is in place, where will be in that particular cycle?
Okay, thank you, Srinath, to bringing it out. Yes, I mean, it is this 11-year cycle, what we call it, it's a sunspot cycle. Just let me go back to my slide to see what I mean by that. Of course, I didn't put any slides on that because I was just mostly concentrating on Aditya related science. So what you see here is the sunspot, which you see as the dark region on the sun. And the number of sunspot as the cycle progresses, it increases to a maxima, and then again it starts to decrease to a minima. So so this we call it as the sunspot cycle. So basically, they count the number of sunspots on the observed, visible light, and then plot those number of sunspots either daily or monthly or yearly. And if you do that, what you see here, what you see as a 11-year cycle, that means every 11 year, the number of sunspot increases to maximum and comes down to the minimum. And we are currently 2023. We are in the rising phase of the number of sunspot. So 2019 is somewhere around the solar minima. We started to increase, and somewhere around 2025, 26 is where we expect it to reach the maxima. So Of course, since L1 phase, Aditya mission is planned, its lifetime is of the order of 5 years. We will be covering a reasonably good amount of the solar cycle. And so we do expect that it may last longer than 5 years. So we would cover at least a half of a solar cycle, definitely with Aditya L1. So we will be, this year when we are launching, we will be getting closer to the Solar Max, which may happen 2025, 26. And a 5-year mission life, if you look at it, it will go all the way up to 2030, 2031, which would be the next solar minima. So we will definitely cover from maxima to minima the sunspot cycle. Why it is important is the sunspot cycle is also related to the activities which I showed you, the coronal mass ejections and solar flares. They also have a relation to the sunspot cycle. So when there is a higher magnetic activity, we do also see many number of CMEs and flares. And the strength of the CMEs and flares also is defined by the sunspot activity. So we do expect when we go to the maxima, we do expect to have more number of flares and CMEs for us to observe. And we also expect that severe storm event may happen during this Aditya period. So which will give us a good sample of data, information for us to understand these events in a better fashion. I hope that covers what you asked for. Yeah.
Thank you.
Sir, one question from chat box. How storm sun makes aurora?
Okay, so that's where this movie, which I played here. So this is even during a normal solar wind, you do have particles streaming into the Earth's magnetosphere and reaching to the polar region. So this is the polar regions, the north-south of the Earth's magnetic field. So even in the normal conditions, the solar wind can reach to the Earth's ionosphere. However, the number of particles which reaches here will be much lower compared to a strong solar wind. When a strong CMEs happen, the number of particles, the density of these particles will be much higher. When the density of the particles is more than a certain critical density, it can interact with the Earth's atmosphere and create auroral events, which basically is nothing but dissociation of the chemical which is present in the atmosphere. And because of these dissociations and recombination, you start to see colorful radiations coming from the Earth's atmosphere. And that's what you call it as an aurora. Basically, what happens is there is a chemical disturbances which happens in the atmosphere. And because of these chemical disturbances in the atmosphere, which can affect the ionosphere and which can affect your radio communications between your technical systems, either on ground as well as in space communications.
Okay. Another question.
So you can unmute to all if anything they want to say. If not question, a general remark within a 5 minutes, not more than that. Just give an opportunity to say something.
There is one question, sir. What the average age of sun in the solar system?
Okay, so sun, as I said, it's in the middle age. It's about 4.5 billion years. We expect it to live up to 9 billion years, roughly. So we are in the middle age of the sun, which is a typical age of sun-like stars, which spend in the main sequence phase of the of the stellar evolution. So we don't have to worry about the end of sun in our lifetime. We have plenty of sun has plenty of energy for us to provide us to live in this planet for a longer period.
Okay.
Yeah, you can allow Dinesh. He wants to speak. Dr. Dinesh.
Okay. Dinesh, sir.
Good evening. Sir, can you tell some more things related to South Atlantic anomalies, like
Okay.
Is
So
that
it's-
not a yes, sir? Please.
Okay, so SAA is a region which is, I mean, if you know space radiations, the major radiations what we initially look at it in the space era is the radiation belts. We have an inner radiation belt and an outer radiation belts, which are not very close to the Earth, which are I mean somewhere above a few hundred kilometers, something like 800, 900 kilometers above it. These are the radiation belts which are contains the charged particles, which enters into the Earth's atmosphere, gets trapped in the Earth's atmosphere, in the Earth's magnetic field. And as it gets trapped, the population also gets increased in certain bands. We call them as inner and outer radiation belts. Apart from these two belts, we also have a South Atlantic anomaly. It's a kind of an anomaly which we think it's because of the magnetic field configurations in the Earth's region, which reaches even closer to somewhere around 200 kilometers. Okay, and which are very close in the equatorial belt, in the equatorial regions. I mean, in the sense, it has a certain inclination, but not exactly in the 0-degree equatorial regions. So, so many of our satellites, when we fly in the low Earth orbit, we need to try to avoid these South Atlantic anomaly, especially when your system is very sensitive for particle energies. So, for example, when we flew AstroSat, we had to choose an orbit such a way that AstroSat satellite doesn't go through this the core of the anomaly. When I say core, it is a region where it is highly densely populated with charged particles, because many of the system which when it sees the charged particles can deposit its energy and either gives you a large background, so and hence your measurement becomes unreliable, or it can even damage the system. So we had to use orbit such a way that we don't go into the core of the SAA. But at certain point of the time, it goes through the flake or the tail of the SAE for a certain time, unless you are exactly in the equatorial orbit. So this is the region where the trapped particles, which gets trapped in a particular region. I mean, the region is expected that it is some kind of a magnetic anomaly, which is happened on the Earth's lower atmosphere, and where these particles are trapped inside. They don't know how to escape out of this. So that's what is called as a South Atlantic anomaly.
Okay, thank you, sir.
Dinesh has a supplementary, maybe, if you can allow. If Shankar.
Sir, thank you. It was nice. And how to monitor this trapped particle concentration, something like that?
Okay, so I mean, of course, we have not sent any missions for that, but there is an international mission. We call it as a RBSP, Radiation Belt Storm Probe. Basically, see, because this is in particular belt, we don't have an orbit which I mean, which is all the time in the belt. So what we do is we go for a highly elliptical orbit, so that when the satellite passes through the radiation belt, it samples the particle at different locations from the Earth, and that's how we map the radiation belts. I mean, if you have looked at the recent papers, there is also a new belt which comes and goes once in a while, and people are trying to understand it, why it is coming. So it is not a simple belt which is just staying there. It is dynamically evolving too. So there is a lot of interest in the international community too to study these radiation belts.
Okay.
I hope that answers.
Yeah, Supriya, check anybody has anything, or else check with the Shankar if it is okay to conclude.
Yes, sir. If any more questions or any opinions to share with sir, I allow everyone to unmute yourself and you can share your opinions.
Excuse me, sir.
Yes,
Am I audible?
Yes,
Jyoti.
yes, ma'am.
Just I want to know what is the difference between synodic and ceridian period of sun.
Okay, again you say synodic and
Ceridian. I think I am not pronouncing properly.
Synodic and ceridial.
Ceridial upset. Huh?
Synodic.
Sidereal and synodic.
Period of sun.
Period. Okay. Period of the sun. Okay. So
Hmm.
I'm also not very clear because I mean I have studied it long time back. I mean probably I think I will. I mean if you can share your email, I will give you more detail.
No,
I'll
I
refresh
think
myself
there was
and
an
do.
experiment in MSc to measure the synodic and sidereal period of sun. Is that
Correct,
your
correct.
opinion, madam?
Ah, yes, sir. Yes, sir. Sure.
One is
Same.
rotation around the earth and another is rotation on its own axis. Maybe if BAK sir is there, if he can also comment, we will invite his comment. Professor BAK, can you unmute, madam? It can be an
Yeah.
open.
Yes, sidereals means with respect to stars, with respect to what is the period of rotation with respect to stars, whereas the synodic is with respect to the sun, that's all.
Yeah, that's.
Sidereal period is shorter compared to the synodic period.
Thank you, sir.
Thank you, sir.
Okay.
No, it was an
Thank you,
experiment in MSc physics. It is there. I think hope it is even now. It may be there, that experiment.
Yes,
Using
sir.
some star charts, they used to measure the periods.
Yes, sir. Yes, sir.
Okay. Supriya, look for the next, madam. Anything?
Any more questions? Okay. Okay. So shall we conclude?
Yeah, just so I'll just want to say that thank you all, and I hope this is a good opportunity for me to interact with all of you. And if any of you are interested in getting into Aditya, I mean, please be in touch with me or Srinath. We will, I mean, tie you with the relevant people, so that as and when the mission and mission data starts to come into play, I mean, you can also play a major role, especially the teachers and the college teachers and the final year students who wants to get into the career in solar and heliophysics. Will be happy to tell you the informations which may be useful for you to I mean take your career in this particular field. Thanks once again. Thanks for the opportunity.
Thank you, Shankar, for your valuable time.
I have sent our WhatsApp group link in the chat box. You can join our group for more updates, and there you can send any information or mail IDs if anybody needed. We will help them to reach you out, sir. Okay.
Okay, sure.
Okay. Thank you, sir. Thank you very much for opportunity to listen your talk. It's a very pleasure to have you on Creactive, sir. Thank you very much, sir. Thank you
Thanks a
one
lot.
and all for joining us. We are closing here. Okay.